All right. What the heck was that video clip about? Well, that was a dramatization of a CIA and Navy SEAL meeting prior to when we went in to get Osama bin Laden, the terrorist behind the 9/11 attacks on the World Trade Center. Forget what movie that is from off the top of my head. I know that Zero Dark 30 is the better one about the same subject, so I'd recommend that. Okay, not the one I showed you there. Okay, what does that have to do with what we're talking about? Well, if you paid attention, at one point they mentioned proportional shadow analysis. Okay, that's what we're talking about, is solving proportions. Basically what happened is once we had an idea that bin Laden was in the compound, we started watching with satellites. And with satellites, it's difficult to measure the height of something from above, but it's very easy to measure the shadow. What we can do then is compare that shadow's length to a height we know, and using proportions, okay, similarity, the stuff we're talking about in this chapter, we're able to say there's somebody in the compound who's 6'5". We knew bin Laden was 6'5", and that was one of the many pieces to the puzzle as to, yep, we think he's here, pretty sure he's here, we're going in. Okay, so when would we ever use this math in the real world? Proportional shadow analysis, and we'll actually show you how to do that later in this lesson. So in lesson 7.3, we're talking about proving triangles similar. Now, we've talked about similarity of shapes in general. In this lesson, we're going to focus specifically on triangles, look at some of the shortcuts we can use with triangles and applications they provide us. All right, here we go with that. So first thing we're going to talk about is this. Let's say I have two triangles, obviously different sizes, but let's say that all three of their angles are congruent. Okay, so bottom left, top, and bottom right match. Okay, now I can't prove that it's true, but what it looks like is true is since the angles are congruent, the triangles are similar to each other, same shape, different size. That's going to be our first postulate for the day. Okay, the angle-angle similarity postulate. It says that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. Okay, we can say angle-angle only two angles because we know by the third angle theorem that if two angles in one triangle are congruent to two angles in another, the third angles have to be congruent as well. So what this is saying is that if we know the two angles are congruent, we know those triangles are similar. They have the same shape, just with different sizes. So first thing we're going to do in this lesson is look at a few sets of triangles and determine whether or not we conclude they're similar, okay, using that angle-angle similarity postulate. Okay, now we've already done some deciding whether or not figures are similar, and to prove it was true we had to look at every single angle to see if they're congruent and every single side to see if they're proportional. Again, this angle-angle postulate is a shortcut. If we know two angles are congruent, the triangles will be similar. Okay, here we're given triangles RSW and VSB. We want to know, are they similar? Now we're given right off the bat that one set of angles are congruent. And here, since these two triangles meet in the middle, we also have a set of vertical angles. Okay, we know anytime we see vertical angles, they are congruent. So what I have here is one set of angles, two sets of angles. So in this case, are the triangles congruent? I can say yes, comma, by the shortcut, angle-angle similarity. Okay, so in other words, by the angle-angle similarity postulate, I know these two triangles are congruent. Let's take a look at another example of determining whether or not triangles are similar. Same thing, are the two triangles similar? Here we're given the actual measures of some angles. We have L is congruent to R because they're both 70. And then notice with this one, they give me the wrong information between these two triangles. They give me J, but not its corresponding angle P. And same thing, they give me Q, but not the K. So what I need to do with this one is either solve for K or P. We could say that angle K is equal to 180 for the total of a triangle. We know the angles always add to 180. minus 30, minus 70. And when I do that, I end up with an 80 degrees. Okay, so what I can see here is that K and Q are not congruent. Now I could do the same thing with the P, 180 minus 70 minus 85, and that would give me a 25 degrees. Okay, not congruent to the 30 here. So since the angles of these triangles don't match up, I know that they can't be similar to each other. So are the triangles similar? We can say not similar. Let's take a look at one more example comparing angles before we move on. Again, are the two triangles similar? How do you know? Okay, here, notice they gave us a few of the angles, but not the corresponding ones. So what we can do is use properties of triangles to solve for the missing angles. Now here I've got isosceles triangles. We know that in isosceles triangles, the angles across from the congruent sides are congruent. So Z would be 68 degrees along with the Y. We can then find X and see if it's the same as A. We could say that angle X is equal to 180 minus 68 minus 68, which gives us a 44 degrees. Okay, again, that's not the same as its corresponding angle, this 62. So again, not similar would be the answer to this one as well. All right, the angle-angle similarity postulate is going to lead to two more shortcuts, the side-angle-side similarity theorem and the side-side-side similarity theorem. Let's go through those here. The side-angle-side similarity theorem says that if an angle of one triangle is congruent to an angle of a second triangle, and the sides that include the two angles are proportional, then the triangles are similar. So if we have congruent angles, A and Q, surrounded by proportional sides, as in AB over QR is equal to AC over QS. So if we have proportional side, angle, proportional side, SAS on these two triangles, then we know the triangles are similar. Okay, that's a theorem based on that angle-angle similarity postulate. We're not going to worry about proving it here. We'll just use it in the next few questions. The next one, the side-side-side similarity theorem, says if the corresponding sides of two triangles are proportional, then the triangles are similar. So as in if AB over QR is equal to AC over QS, which is equal to BC over RS, if all three sets of sides are proportional, then I know those triangles are similar. Let's go ahead and use those theorems or use those shortcuts to determine whether or not we're looking at similar triangles. So problem 2, same idea. Are the triangles similar? If so, write a similarity statement for the triangles. Okay, so here I've got two triangles. I've got the smaller KLP within the larger KMN. Now the trick with this one is notice both those triangles share an angle here. They share this angle K, so that's one congruent angle. Now I know that the lengths of the sides that include that angle, okay, 8 and 8 plus 2 equals 10 in the case of the larger triangle, and same thing 12 and 15 for the bottom side. So what I have here are the angles and sides. What I need to see is if those sides are proportional. If they are, I can say that yes, these triangles are similar by SAS similarity. Okay, so let's go ahead and look at those sides here. For the smaller triangle we can look at KL over MK. We'll say that again, KL over KM. That's equal to an 8 over KM will be 8 plus 2 is 10. Now when I reduce that down, 8 and 10 are both divisible by 2. Dividing both by 2, we get 4/5. And we want to see if that's proportional to the bottom side. In other words, do we get the same fraction when we look at Kp over Kn? Kp is 12. Kn would be 12 plus 3, 15. And reducing those, I can divide them both by 3. That's going to give me a 4/5 as well. So we have a congruent angles surrounded by proportional sides. So are the triangles similar? We can say yes by SAS similarity. So as in by the side angle side similarity postulate. And as far as writing a similarity statement, we'll just name the two triangles. We can say triangle KLP is similar to triangle in the same order then KMN. All right, so answer to this question will be yes or no. If it's a yes, how do we know? Which shortcut do we use? Well, this one is an example of the SAS similarity, and then here we're also giving the similarity statement. Let's do one more checking if triangles are similar problems. Again, 2B, are the triangles similar? If so, write a similarity statement for the triangles. Okay, with this one, notice they didn't give us any angles, so it's obviously not going to be by angle, angle, or side, angle, side. But I've got all three sets of sides. So this will either be a no or yes by side, angle, side. Let's start taking a look at those sides here. We can start off with the biggest side, US and WX. That's equal to a 10 over 15, which reduces down to dividing both by 5, 2/3. Okay, we want to see if we get the same thing with the other sets of sides. Let's look at the medium length side next. UT over WV. That's equal to an 8 over 12. Both those are divisible by 4, so that'd give me a 2/3 as well. And then issue with this one as we look at the third sets of sides, ST over VX, we end up with a 6 over 8, which if I divide both those by 2, we get a 3/4. Okay, that's not the same as the ratio we got in the first two cases, so I'd say these sides are not proportional. Okay, so the SSS didn't work for this one. Are they similar? We'd say not similar in this case. All right, that's what it looks like when a triangle doesn't pass that proportionality check. We don't get the same ratio for all the sets of sides. All right, last thing we're going to do this lesson is get into some applications of similar triangles. We're going to talk about something called an indirect measurement. That's just a way of measuring objects that are difficult to measure directly. Okay, so in the case of our proportional shadow analysis, that was an indirect measurement we made. We didn't actually go down to the ground and physically measure Osama bin Laden. Okay, we measured him indirectly by looking at his shadow. So we're going to take a look at two indirect measurement tricks we can use that both use similar triangles and are both actually very simple to use. First one involves measurements and a mirror. Problem 3 part A says, before rock climbing, Darius wants to know how high he will climb. He places a mirror on the ground and walks backwards until he can see the top of the cliff in the mirror. Okay, he's also got a few dimensions measured out. What's the height of the cliff? Okay, so the idea of an indirect measurement is there's something that's difficult to measure. Okay, the cliff in this case. We don't want to have to climb to the top of it and drop a tape measure down to figure out how tall it is. We like to know how tall it is before we climb it. So instead what we'll do is we'll measure things that are easy to measure directly. Okay, it would be easy to use a tape measure and find this 34 feet or this 6 feet. Okay, or we could just pace it out. You probably know how tall you are or how tall your eye level is. And the trick with this problem is if Darius positions himself so we can see the top of the cliff in the mirror, a physics property is that I know these angles of reflection will be congruent to each other. So what I have here are two triangles with one set of congruent angles and another set of right angles which are congruent. So I know by angle-angle similarity these triangles are similar, therefore their sides are proportional. So what I can set up to solve here then is I can take 5.5 over 6 and set that equal to the x we don't know over the 34. All right, and how they set this up was height over distance in the mirror of the little triangle. Okay, equals height over distance in the mirror of the big triangle. Cross multiply, 6 times x is just 6x, is equal to 5.5 times 34. That's going to give me a 187. All right, divide both sides by 6, and we end up with x is equal to 31.2 feet, we could say. All right, so there's our mirror indirect measurement trick. All right, we're going to finish the lesson off coming back to our proportional shadow analysis idea. So here's a way we can use indirect measurements, similar triangles, and shadows to measure difficult stuff. Problem 3 part B says, in a garden, a bird bath that is 2.5 feet tall casts a 1.5 foot shadow. At the same time, an oak tree casts a 90-foot shadow. How tall is the oak tree? Okay, let's draw out what we got going on here. And you're going to see why I'm a math teacher, not an art teacher. So we've got a oak tree. We're not sure how tall it is, but it's easy to measure shadows along the ground. We know the shadow is 90 feet. And at the same time, we have a bird bath, which is 2.5 feet. And it casts a 1.5 foot shadow. Now, how this relates to triangles, well, where are those shadows coming from? Well, they're coming from the sun. Its rays hit the top of our object and form a triangle with the edge of the shadow. Now, we can assume both the tree and the bird bath are coming out of the ground at right angles. They're both right triangles. And then key for this problem is at the same time of day, the angle of elevation to the sun will be the same. So once again, I've got similar triangles by angle similarity. Therefore, again, I know the sides are proportional. Okay, so we can set our proportion up as x over 90. So height of the tree over shadow of the tree is equal to 2.5 over 1.5. Height of the bird bath over shadow of the bird bath. Okay, again, cross multiply. X times 1.5 is 1.5x is equal to 90 times 2.5, which will give us a 225. All right, cross multiply and divide both sides. Divide by the 1.5. And that leaves us with x is equal to 150 feet tall for the oak tree. Okay, again, simple indirect measurement trick, much easier than actually climbing to the top of the oak tree and dropping a tape measure down. All right, that's it for lesson 7.3, similar triangles. Give that Math Excel a shot. Okay, get some practice in. We'll be here to help you if you need it.